All right, the next example that we have, example 5, is all about what to do if our path C over which we're integrating is a little bit more complicated. And it doesn't have to be terribly confusing, but even even having a path that's maybe broken apart over a few different smaller paths can make things a little bit more work, but it is always possible to do. So, with that being said, let's take a look at it. We're given a vector field, capital F, and C, our path over which we're supposed to find this integral, is the triangle in 3 dimensions whose vertices are these 3 points. And we are going to orient it this way. So we're going to start at the point 1, 0, 0, move towards 0, 1, 0, move towards 0, 0, 1, and then we'll loop back around since it is going to be a triangle, so it is a closed path. So first thing I would do is I would draw this. It does not need to be perfect. This is just a sketch to help us frame ourselves. So here we have our standard x, y, z axes in 3-space. And then let's go ahead and draw our path here. So let's say we do something like this. There we go. So we've got 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we're going to go ahead and orient it this way. So I'll just mark in blue that we're going to start here. So since we have 3 different paths, really, we have 3 distinct straight line paths, there's not an easy way for us to combine all 3 of these paths into one formula or one parameterization, because notice here that it's a sharp turn. It's not a continuous, it is a continuous, but it's not a differentiable transition. So because of that, it's easier to just parameterize this path, this path, this path, and do 3 separate integrals. So the first leg of the journey, I'll call this subpath C1, followed by C2, ending of C3. So what we have here is that our path our path C is C1 union C2 union C3. So you can think of this symbol union as also like gluing together. So if we glue C1 to C2 to C3, we'll get the full path C. So this full path here we'll call C. So let me just make that like a definition. So let. So once we have that, we need to go ahead and describe these paths. So what we want to do here is get the direction vectors. So let's go ahead and do this one at a time. So for C1, ooh, that's large. Let's go back. So for C1, we'll have R1, which will be our starting point, 1, 0, 0, plus t times our direction vector. So our direction vector, we could just do final minus initial. So final minus initial. So this will be 1, 0, 0 plus t times the vector negative 1, 1, 0. All right. C2, which will be R2 of t. This will be 0, 1, 0 plus t times, I won't go through all the motions again, we should just be able to get the fact that our y component is going to decrease and our z component is going to increase. So we'll get that. You can go through it and verify that it's true. It is. And then C3, we'll have R2. Oh, sorry, excuse me, R3, I should say. R3 of t. This will be the point. We're going to start at 0, 0, 1 plus t times we're going to increase x and decrease z. So one thing we can do here is actually go ahead and combine these so that we get one vector expression. So this would be 1 minus t, comma 0. This would be 0, 1 minus t, comma t. And then we'd have t, comma 0, comma 1 minus t. And all of these are for t between 0 and 1. Whenever you parameterize something like this, where you do final minus initial for your line, then your range will always be 0 and 1 if you do it in that way. So that was a bit of work to get all of that, and that's what makes this tricky, but it is possible. So once we have all of that, we can go ahead now and do our composition. So ultimately, the integral over c of this vector field, e to the z, e to the y, x plus y, dot dr, this, we can actually split this up into the following. This would be, essentially, let's just make our lives a little bit easier and copy this down, and then copy paste a couple times. So the first one, this would be over c1 plus what we get over c2 plus what we get over c3. That is a bit of work, but let's go ahead. The nice thing is, all these integrals here are over the same range. So let's also put a little divider here. Okay. I don't want to get confused, so I'm going to just go ahead and divide that off really quickly. All right. So then, we'll continue here. Equals, all these integrals are from 0 to 1, because the range for t happens to be the same. So, 0 to 1. And now for this integral here, this is e to the z, and what we want to do here is look at our r1. So here's r1. What's z? Z is 0. So this is e to the 0, comma e to the y, which is t, comma, we're going to have x plus y, which is 1. Dotted with, we need to take the derivative of this expression and put that here, r1 prime. So this would be negative 1, 1, 0 dt plus, again, integral from 0 to 1. Here we have e to the z again, right? Because this vector field isn't changing. What's changing are x, y, and z because our paths are different. So on this path, z is t. So we'll have e to the t, comma, e to the y, and y on this path is 1 minus t. Lastly, we're going to have x plus y. So we want to add these two together, the x and y components, to get 1 minus t. And we're running out of room here, so why don't I go ahead and just, how about we just delete this full thing? So we have 2, we just need the third one. Well, we're almost done with that one. I'll keep this up here for a moment. So what we need to do is multiply by the derivative of R2. So dot it with R2 prime. So R2 is right here. So that would be, the derivative would be 0, comma, negative 1, comma 1. 0, negative 1, 1. dt. Lastly, another integral from 0 to 1, e to the z. Z for this R3 is 1 minus t. E to the y, well, y is 0, so e to the 0. And x plus y, we're going to add these two together to just get t. We're running out of room, so I'll move down a line. The derivative is 1, 0, negative 1. That's a lot. But since everything is an integral of t with respect to t from 0 to 1, we can just make this one big integral and add together the integrands. So let's go ahead and do our dot products. So this would be, let's go through and simplify these first. So that's 1. That's 1. Okay. So then we'll have 1 times negative 1, which is negative 1, plus e to the t plus 0. Moving on, we'll have 0 times e to the t, 0. So then we'll have minus e to the 1 minus t plus 1 minus t. Here we'll have 1 times e to the 1 minus t plus 0 minus t dt. Much better. Go through and simplify all of this. This should, at the very end of the day, give us e to the t minus 2t dt. Right, because these will cancel. The negative 1 and 1 will cancel. So here you can see we have negative t, there's our negative 2t, and we're left with a single e to the t. So integrating this, we should have e minus 2 as our answer. But the big idea here is that if you have a complicated path, you can split this up into smaller, simpler subpaths, integrate over each one, and add the results together in a consistent way.